this is one of the equations we already seen, right?
Yep.
So if we're trying to
Not one that we derived.
just get it. Hold on.
Yep.
That should be easier. As in relation, we have like we're trying to find wavelength, and we have a speed of the object plus its mass.
Mm-hmm.
You multiply those two, you don't really get wavelength.
So, de Broglie equation is the wavelength is equal to Planck's constant times the mass, sorry, Planck's constant over mass times velocity. That's it, we just plug in the numbers and that gives you the wavelength. So this would be 6.626 times 10 to the negative 34 joule seconds divided by mass. Now remember, joules is kilogram meters squared second squared. Okay? A joule is kilogram meter squared second squared. Okay, so when we're all done, wavelength is meters, so we should have meters when we're all done. Okay, so mass, the joule has kilograms, so we need mass to be in kilograms. This is where people generally this is where the mistake happens. Mass here is in grams. We can convert that straight into kilograms, 0.145 kilograms. Right, that's my mass. Times the velocity. Now, the units here are in seconds, not hours. So I need to convert my time into seconds. And this is miles, which is a useless unit. We want it in meters. Okay, so we're going to take our value, 92.5 miles per hour. Okay, we have a conversion for kilometers per hour. So that would be times 1.6034 kilometers per hour to 1 mile per hour, right? So that's going to give us kilometers per hour. Okay. We want meters per second. So let's convert the kilometers into meters. Right now it's kilometers per hour, so kilometers is on top, hours is on bottom. So it's 1,000 meters per 1 kilometer. The kilometers are going to cancel out. And so I have meters, and then this is hours on the bottom. Getting hours into seconds. 1 hour is 60 minutes. 1 minute is 60 seconds. All right, so hours cancel out the hours there, minutes. And so now on the bottom, I got meters over seconds. If we look at our units, this part here is going to cancel out one of the meters and one of the seconds. This second here will cancel out the other one, giving me just kilometer meters. And then this, kilogram meters. This kilogram will cancel out the kilogram, giving us just meters in the end. Plug it all in, we get a wavelength that's equal to 1.105 times 10 to the negative 34 meters. So the wavelength is ridiculously small. To get an idea, we already calculated the Bohr radius, right, which is the distance between the electron and the proton, the nucleus, right? The Bohr radius was 5.29 times 10 to the minus 11. Yeah, minus 11 meters. right? So the wavelength of the baseball, the reason that you don't see wave-like behavior of a baseball that you're throwing back and forth, even if you can't throw it at 92.5 miles per hour, is because the wavelength is 20-ish or 23 orders of magnitude smaller than the distance between an electron and the proton in a hydrogen atom.
Wait. So if you were to just kind of like zoom in, pretty well in, right? And if you just kind of observe the baseball, it would actually move as a wave.
It would have wave-like behavior, yes. But the wavelength, how much it's fluctuating by, is 23 orders of magnitude less than the distance between an electron and a proton. So, yeah, you're not going to see, that's why you don't see wave-like behavior in everyday objects, is because most of the wavelengths are in that ballpark range.
So basically, everyday object, everything has a wave like
Mhm.
like properties.
Yep.
But because it's always so many magnitudes smaller than the actual radius of atom or nuclear proton to like electron,
Mhm.
you can only see it manifest into like actual observers.
Yep. But if you're talking about individual atoms, right, they don't have much mass, right, and an electron has even less. So that's why the wave-like nature of atoms, electrons, and photons matter, and that's because their mass is so darn small. And the number that goes in right there is really, really small. And so you end up getting wavelengths that are on the order of the actual size of the thing that you're looking at. And so the wavelength of an electron is in the ballpark of the radius of the the Bohr radius. So for stuff down on the atomic scale, it starts to matter. For everyday objects, it doesn't matter at all. Okay, so that's why baseball, when you're swinging at it, it doesn't actually phase into behaving like a wave, and you can hit it with a bat. It's because it doesn't. The wavelength is so small as to be irrelevant. Okay, so postulates of quantum mechanics, and sort of giving this as a guide of where we're about to go. So up to this point, we've been trying to show why quantum mechanics is important, how it patches up a bunch of holes, and how, like for the Rydberg, if we use the Bohr model, we actually predict the Rydberg constant pretty well spot on, right? So what the patches that we were able to do by quantizing energy, when we're looking at stuff on that atomic scale, right? Behavior like an electron getting excited, moving somewhere, or photons being absorbed, or in the case of heat capacity, molecules jostling around in a crystalline state, right? Stuff on the atomic scale, where it's dependent on the atomic scale motion. Applying this idea of quantization fixed the problems that we had, right? So quantum mechanics is takes over for classical mechanics. But if quantum mechanics actually works out, one of the things that has to happen is everything that was explained by classical mechanics has to also be explained by quantum, right? If quantum can't explain everyday stuff, then it's also very wrong, right? It works well at a small scale, but is wrong at a big scale. So for quantum mechanics to be reasonable, it has to work on the full scale as well. So some of the postulates of quantum mechanics are, and when you're thinking about postulates, it's the stuff that can't really be proven, but if you assume it to be true, it then leads to your equations. So one of the postulates of classical mechanics is force is equal to mass times acceleration. You never actually prove that force is equal to mass times acceleration. You never prove it. It's something that's taken as given, right? So these are similar to that. So in classical physics, force is equal to mass times acceleration. You never prove it.
Wait, really? No one proved that?
Yeah, no, it's taken as given.
So whole physics, it was just like a big assumption.
Yeah. But everything fits. So if you make that assumption, all these other things work out. So that suggests that your assumption was valid until you start looking at quantized stuff, right? So for quantum mechanics, this stuff isn't proven, it's taken as given, and then everything falls out of it. Okay, and some of them actually make sense, like number 2, every observable, well, no. Well, we'll go through. So the states in quantum mechanics system are completely specified by a wave function. We'll get into what a wave function is, but there's a function that specifies the wave-like behavior, called the wave function. And if you know the wave equation, that wave equation specifies everything. So the electron behaves according to a wave equation. You can take derivatives, integrals, whatever. Any behavior of that hydrogen atom that's being the electron that's being specified by that wave equation, plug that wave equation into all the other equations and you get out the real values. So essentially, if you know the wave function, you know everything, right? Whereas classic physics, if you know the force acting on something and its location, you know everything, right? It's the same sort of a postulate, right? Every observable in classic mechanics has a corresponding, we'll get into what both these terms mean, a Hermitian operator. It's a very specific type of function, right, in quantum mechanics. Essentially, everything that we used to have in classical mechanics has to be explained by quantum mechanics. And there are a very subset of mathematical functions. An operator is essentially just a fancy term for a mathematical function. Hermitian, we'll get into it. Okay, once we get into it, it makes sense. So there's a particular type of function. Anything that has a real value has to be one of these types of functions. Okay, any measurement of an observable associated with an operator, and we're going to use this little hat, look like a caret above a variable. It's a function or an operator. The only values that will ever be observed are eigenvalues, which satisfy the equation operator operating on a wave function is equal to the eigenvalue times the wave function. We will get into what eigenvalues are. It's just a fancy word that's math-based, not chemistry-based. So the eigenvalues and eigenfunctions are mathematical terms, not chemistry or physics terms. Okay? And it's all covered in a couple slides and as well as in your book. If a system is in a state described by a normalized wave function, we'll get into what that is, then the average value of the observable corresponding to that operator is given by this particular function. We'll get into all that why. I swear this will all make sense soon, right? But this is sort of giving you the guidepost of where we're going, right? So essentially, the stuff we're gonna get into in just a sec, this is what it's all for, and then we're going to explain what all these terms mean. Okay? The wave function of a system evolves in time according to the time-dependent Schrodinger equation, which looks like that. The total wave function must be anti-symmetric with respect to the interchange of all coordinates of one fermion with those of another. We'll get into what all that means. I swear it'll make sense. Right now it sounds like gobbledygook, but these are all just, most of them are mathematical terms, mathematical names. Okay, Heisenberg uncertainty principle, right? So quantum is where stuff gets weird, right? And this is one of the weirdest things of quantum mechanics. Okay, so in classical mechanics, the center of mass of a particle always has an exact location. If you can see it, you know where it's at. Quantum mechanics, no. If you can see it, you don't actually necessarily know where it's at. There's really weird behaviors. Particles follow a trajectory with an exact position and momentum at all times. What that means is, if you know where an object was at any point in history, and you know the forces acting on it, you can predict where it's going to be in the future. Quantum mechanics, you can't. Right? And the reason that that works out for classical mechanics is this reason here. The wave-like behavior of objects that were studied using classical mechanics is negligible. You don't actually see any wave behavior on a baseball. But when we're dealing with stuff on the quantum scale or on the atomic scale, wavelength starts becoming, it starts mattering. Right? The scale of the wavelength is similar to the size of the object, and so the wave-like behavior starts to matter. So as long as you're talking about stuff that's in the kilogram-ish range, you know, even a hundredth of a kilogram going in here still is going to give you a negligible wavelength. But once you're talking, you know, atomic, like an individual atom or an individual electron, the wavelength starts to matter and you start having wave-like behavior. So in quantum mechanics, because of the wave-like behavior, Heisenberg stated in 1927 that no matter how the experiment is done, there is a minimum uncertainty in a trajectory. So if you're looking at stuff on, well, actually anything, but particularly stuff on the quantum level, or the atomic level, the uncertainty in the momentum times the uncertainty in the position has to be more than, greater than or equal to our h bar, which again is h divided by 2 pi, over 2, right? And we're actually going to derive, probably next week, maybe Thursday, but more likely next week, we're going to derive Heisenberg's uncertainty principle. We're going to show why it has to be based on things acting like a wave, right? So you don't necessarily have to take it as given. We're going to show that that's the case. Okay. Now the reason that this is the case if you're trying to probe something's position on the atomic scale, let's say we're trying to figure out the location of an electron, right? Or the location of something. There's a couple ways of probing where something is located. So if you want to know the momentum, or well, let's start with the position. If you want to know the position, you have something. The way that you're going to find the position is you're going to fire the thing that will give you the least amount of change or the least problems is firing a photon. Right? Photons don't typically have a lot of energy, so if we fire a photon at something that is a very small particle, we'd fire a photon at it, and it would have to collide, and that would tell us where it was at. Right? But to figure out momentum, you need to know where it was at time 1 and where it was at time 2. Right? So you have to measure where it started with and where it ended with. But as soon as you measure where it is the first time, you're going to impart whatever energy was in the photon onto the particle, and now it's moving off in some other direction at a different momentum than it originally had. So we can lock down the position really well, but in doing that, we're changing the momentum. Right? So in order to figure out where it's at, you have to probe it somehow. Right? You have to figure out where the position is. The least problematic way is using photons. Right? So using a photon, the photon hits, and that's going to change the momentum. Right? So we can know the position. The more we know the position, so in order to figure out the position, you'd want a shorter and shorter wavelength. Right? But a shorter and shorter wavelength means higher and higher energy photon, which means you're going to disturb the momentum even more. So the more accurately you know the position, the way that you would determine the position accurately would be a very short wavelength. So the more accurately you know the position by using a shorter and shorter wavelength of light, you're hitting it with higher and higher energy photon, which means you're changing the momentum by more and more. So the better you get this delta x, the more you're affecting it in the delta rho. The way that you would figure out the momentum, conceptually, a lot of times the way momentum is figured out is you know how much an object weighs. So what they do is you have what's called a chopper. So it's essentially you have a wheel with a slit in it, and you have another wheel with another slit in it. All right, and you fire something through. You might fire a stream of things through, one after the next after the next. When it goes through this slit here, so it either collides with your chopper. So a chopper would look kind of like that. It's a wheel spinning around. Your object that you're trying to determine the momentum of, you fire it through, so it's going somewhere in this location here, right? It comes down the tube, and then it makes it through this other chopper, right? And so determining based on how fast it's moving, it will either get chopped by, if it makes it through the first one, then it either gets chopped by the second one or not. If it makes it through, then you know how fast it was moving. But the more you reduce the size of this, the less well you know, or the less likely you are to get something to go in. Right, so the uncertainty is, once it goes into the chopping machine, the more precise you shrink it up to determine the momentum, the less certain you are as to its current location inside the box. Right, so those are the two examples that are commonly given for why you can't know the momentum and why you can't know the position. The momentum, if you determine it really well based on the choppers, in order to determine it really well, you have to move these further and further apart. Right, the further they are apart, the better you are at selecting for a particular velocity. Right, but if you're selecting for a particular velocity, you don't really know when it entered in very well and when it exited out very well. So the uncertainty then becomes, where is it inside? Now, we're going to actually, like I said, we're going to derive or show how Heisenberg's uncertainty principle falls out of the wave-like behavior. But for now, or at least this class period or the next couple, we're going to be using Heisenberg's uncertainty principle as being the better you know one. So if this one gets smaller and smaller, this one has to get bigger and bigger. So this part here, delta rho, your uncertainty in your momentum times the uncertainty in your position is equal to or bigger than Planck's constant over 2 pi over 2.
What was the first scenario? Like you can't know the position of the particle, right?
Yeah, so the way that you would measure the position is by using photons of light. When you find, to determine the exact position, you'd have to hit it with the photons. As soon as you hit it, you impart new energy onto it because photons have energy, and they would come off with a new momentum. And so you wouldn't be able to determine the position that it had at this point plus the momentum that it had at that point at the same time.
You can't really infer how much it would impact it with, or?
No?
Alright, so if you had a particle somewhere, right, and you
Mhm.
just beam the photon to it,
Mhm.
you would know how would it react to the photon. Because like you know how much energy the photon puts it on the particle, right? The first diagram that you had, right?
Yeah.
It was like a particle, and then you shine the photon onto it, and then you don't know the position. You don't know the second position, right?
So you would know the position
Position
because, well, by shining a photon on it, you're hitting it with a photon, you now know where it was at,
exactly.
right? But you don't know what the momentum it had before the photon hit it. Because once it absorbs the photon, it now has all the extra energy of that photon, and it goes off in some random direction.
Why the random?
Because that's just.
Because like you would know, okay, let's just like scale it to classical, right? Let's say if that was a object,
Mm-hmm.
and that was some kind of force, which is a photon.
Mm-hmm.
If you applied it at a certain angle or a certain way, you would know where it would go.
Yes, but that's because on classical size, it doesn't have a wavelength. We'll get into exactly what it all means.
Alright, let's say,
Okay.
just for theoretical purposes, let's say that particle absorbed all the energy of a photon, right? And then
Mhm.
it's moving a certain direction with certain energy. Why can't you just do it again? Just shine another photon into it, wherever it absorbs, that's the next position. No?
That's where it is at the second time.
Yeah. So you had now.
But what was the
it's-
original momentum?
The first position. Alright, you shine the photon into it, right? And it interacted with the particle.
Mm-hmm.
You know the position at that moment.
Mm-hmm.
Then it moves somewhere, with a certain velocity. You shine another photon into it, wherever it interacts, that's the second position.
Mm-hmm.
Now you have first position, second position, so you know how to move from one place to another place, no?
But you don't know the momentum that it had originally. So at the exact instant that it was at this location,
Mm-hmm.
you don't know what the momentum is because by hitting it with
Oh,
the
you can't just
photon of light,
oh.
so you can't know them both at the same time. You can measure one, but you don't get the other. The other problem is, and we'll see this, is this doesn't actually have a position.
It's probability, right? Yeah.
It's a
But you
probability
can
cloud.
never have a particle be stationary at all.
Hmm?
You can't have that particle just be stationary in space. So you really don't know the first position either. You have probability of where it's gonna be. Whatever.
So, this brings us into the trick of quantum mechanics. If you try to visualize stuff on the atomic scale, you're going to get frustrated. Right?
Should make sense, but it's not.
It won't. Right? And the reason it won't make sense is because our everyday experience has nothing that behaves as a particle and a wave at the same time. There's nothing that you've ever interacted with that on like a visible, like macroscopic scale has particle wave-like behavior that has a noticeable wave. Right? Things that you interact with, they do have a wavelength, but the wavelength is so darn small that you can't see it. Right? You never actually see anything that has both particle-like behavior and wave-like behavior at the same time.
Light?
Hmm?
Light?
You can look at it either as a particle or as a wave.
Oh, it's like once you observe it, oh, okay.
Yeah. And we're going to see that what's called is the superposition collapses. It's the terminology for it, but that is down the road. The interesting thing is they're actually using those behaviors of the what's called the collapse of the superposition to encode packages of information using the quantization of what is it, photons going through, or energy going through like a signal. So you can actually use quantum mechanics to like super encode for like super encryption your message. So you can actually tell if someone's listening in on you, because in order to listen in on the message, they have to observe the message, and by observing the message, you collapse the wave equation, and it makes it so that someone on the other end can tell that someone looked at it in between. It's absolutely bizarre.
Is that like uncertainty due to like just not being able to measure it precisely, or just it's gonna be there no matter what?
It's there no matter what.
What's the
It is a limit on how well we can know stuff. So the better you know the location, the worse the momentum is going to be. And the better you know the momentum, the worse the location is going to be. Now this is a really small number. Right, h bar, well h is 6.626 times 10 to the negative 34, which means you can still know stuff pretty darn well. But the uncertainty in both position and momentum is not going to both drop to 0. And that is one of the weird ways in which quantum mechanics behaves differently from classical. Classical, you can know something, you can know the forces on it, so you can predict where it's actually going to be. In quantum mechanics, it's all based on probability. Okay. So let's actually take a look at our minimum uncertainty in two things. And this is H bar.
And the second one is like picometer, or is that PM? Or is it P?
No, this?
Yeah.
Yeah, picometer. So where the 100 picometers come from, so you got a hydrogen atom, radius here, we already worked out was 50 picometers, or 52.9. So twice that.
So what do you actually solve it for?
Delta V. Well, let's work through the first one. All right? So the minimum uncertainty would be when this is equal to h bar over 2, right? This, the uncertainty in each one of these has to be bigger than or equal to. So the smallest it could possibly be is equal to. Right? So what we're going to do is we're going to say mass times the change in velocity times the change in position is equal to h bar over 2. To solve for this, that would mean that the change in velocity is equal to h bar over 2m times our uncertainty in x. So that would be 6.626 times 10 to the negative 34 meters squared, kilograms, seconds negative 1 over 2 pi, right, because it's h bar, divided by 2 times the mass. This one is copper sphere, so that would be times 0.0010 kilograms times our change in x, which is, so we want it to be in meters, right, because this value up here is in meters. Right? So that would be 0.1 times 10 to the minus 3 meters. When I do that, I get 5.2 728 times 10 to the minus 28 meters per second. All right, so what that tells us is that if something has, a decent amount of mass to it, realistic, if you're talking atomic scale, this is a huge uncertainty, right? If we're talking real world size, that's pretty good, right? Knowing something, where something is down to the millimeter, like in a room, right? It's, specific distance from me, and I know it down to the millimeter. That's a pretty good measurement. The velocity, we can know it, that's crazy good, right? You can know it down to that many meters per second. So in classical physics, we can know stuff really, really accurately compared to our everyday units of measure, right? The problem is once we get down and think about it in terms of the atomic scale, knowing where an atom is down to the millimeter, that is terrible, right? Because atoms are on the scale of picometers, and so if you know its position, that's 10 orders of magnitude off of its radius, knowing where it's at. It's like having a football somewhere in the United States, right? I know its position down to it's somewhere in the continental United States. It's terrible, right? But in terms of our everyday measurements, and interacting with us, we know fairly what we would consider accurate, and we know its velocity very accurately. For the second one, let's say we're talking about an electron, and we know that it's somewhere in the hydrogen atom, diameter, which is, makes sense. We know what's in there. So what's the uncertainty of how fast it's moving? We can do the exact same thing, right? Plugging in the same values. The only real difference are going to be these two bottom numbers, right? So 6.626 times 10 to the minus 34 meters squared, kilograms squared, second minus 1, over 2 pi. 2 times, it's an electron, right? So we're going to use the mass of an electron, which is 9 point, I guess this one, I grabbed a slightly more accurate value, 9.110 also works, times 10 to the minus 31 kilograms times 1 times 10 to the minus 10 meters. All right, technically, this has 1 sig fig. So this is 5, 7, 8, 831 meters per second, or 6 times 10 to the 5th meters per second. Okay, so we know the electron's somewhere in the hydrogen atom, but our uncertainty in how fast it's moving is a reasonable fraction of the speed of light. Right? So the reason why we bring this up is, let's say you're relying on having some form of position and velocity known really well. There's a cap on how well you can know the position and the velocity of an atom, and that's bound by the Heisenberg uncertainty principle. Right? So if you're relying on knowing if you're trying to do an experiment, right, and you want to figure out the velocity of an electron, and you want to shrink it down to half of the size of a hydrogen atom, the limit on your velocity is going to be terrible. Right? You're not going to be able to know the velocity really well at all.
So like uncertainty is like basically plus or minus that much. Like even though if you know the position that well, velocity is going to be off by either plus down or minus as.
Yep. But if it's moving at 10th the speed of light, that's 2.998 times 10 to the 8th. This is times 10 to the 5th. So you can still know it fairly well, but that's the uncertainty. That's the best you're gonna get. Likely the uncertainty is gonna be higher than that. But figuring out the best set of experimental parameters, that is the best you're ever gonna get, is that. Okay, that is time. So we will pick up here the next time. We're gonna get into what all those weird words meant.